A genetic algorithm example. What is the square root of 81? We are assuming that we do not know how to calculate it, which seems absurd as everybody knows that it is really equal to 9. But if you do not know the algorithm and you do not have a calculator, could you find the square root of this number? 14949922779169. I hardly believe so. The system randomly generates, by using a random number generator, strings of bits that might be the answer. In practice, we generate hundreds of them, but for our example, we'll use just 3. So let's assume these were the numbers that were generated. A is 1, 2, 3, 4, 5, 6, 7th one, and the 1 which equal 1 in the decimal presentation. B is 11101110, which equals 238 in the decimal presentation, and C is 11110010, which is 242 in the decimal presentation. We also define a fitness function, which we'll call FF, which equals the absolute value of 81 minus the gene value multiplied by the gene value. And we want to minimize this value. Why? Because if we find out the gene value is 9, the 9 square is 81, 81 minus 81 is 0, and we have our answer. Testing this fitness, we find out that A equals 81 minus 1, which is 80. B is absolute value of 81 minus 238 multiplied by 238, which is 56563, and C is absolute value of 81 minus 242 multiplied by 242, which is 58483. None of this result is a good fit. None is even close to the solution. But nevertheless, A and B are more fitting than C. So we assign them a higher probability value to pass to the second generation. Again, we perform a lottery. And let's assume that the strings A and B indeed succeed in passing to the exchange cycle. Again, using the random number generator, we try to find a cutting location. And the cutting location turned out to be after the 5th bit. Thus we have A is 1, 2, 3, 4, 5, 0, 0, 1, and B is 1, 1, 1, 0, 1, 1, 1, 0. We exchange the tails. This goes here, and this goes here, and we get a new answer, A prime equal 0, 0, 0, 0, 0, 1, 1, 0, which is 6 in the decimal notation, and B prime, which is equal 1, 1, 1, 0, 1, 0, 0, 1, which is 233 in the decimal notation. Let me scroll up the screen. Again, we are far off from the results. Here by 45, and here by 5400, 248. But please note that if these strings, A prime and B prime, succeed in getting to the next generation, and if we are lucky in having the cutting position after the 4th bit, we then will get A prime equal 1, 2, 3, 4 zeros, 0, 1, 1, 0, and B prime will be 1, 1, 1, 0, 1, 0, 0, 1. And again, we change the tails. This goes here and this goes here, and we get a new result, which I now write in red, which is A prime prime equals 0, 0, 0, 0, 1, 0, 0, 1, and B prime prime equal 1, 1, 1, 0, 0, 1, 1, 0. This is 9 in the decimal notation. This is 230 in the decimal notation. Again, we'll examine them, so our fitting functions, and we find out that ff is, for the case of A prime prime, it is absolute value of 81 minus 9 multiplied by 9, which is 0. And for the case of B prime prime, it is 81 minus 230 multiplied by 230, which is 58199. Thus, A prime prime equal to 9 is indeed the answer. In our example, we use binary strings, but they do not have to be so. Other precision can be used. And by the way, the square root of the large long number that we had at the beginning is 3866513. Bye bye.